So, what we finished up doing last time, was we finished up talking about modules over PID. And what we're getting into now is one of the applications of this. We talked about the decomposition, we talked about, really the classification of finitely generated modules of the principal ideal domain. It has a free part, and then it has a torsion part, and you can write this in a specific way. Consequence of that is the fundamental theorem of finitely generated Viennese groups. And here's another application that we do. We're looking at a single linear transformation, phi from E to E. A is a matrix over the field K, n by n. So under the situation here, we have the following. There exists a unique monic polynomial of AX, such that Q annihilates B, and this Q phi divides every polynomial that annihilates B. There exists a unique polynomial QA that annihilates the matrix A we speak of. And QA divides every polynomial that annihilates this matrix. And here's the connection. If A is the matrix phi relative to some basis for E, then these two polynomials are in fact the same. Okay, so let's get to this and point out why this is true, and then see what this is all about. So let's first remark here that as a vector space over K, Kx is infinitely. I think we can all agree with that. In fact, you can think of a basis for this is how that it's 1x, that's 3x. These are all linearly independent over K, and this is actually isomorphic too. The correct sum, right? In fact, think of the 0th place is the constant term, the 1st place is the x one term, 2nd place is the square term, so forth. Every polynomial has a degree, which means that this is actually a direct sum. That is, after some point, all the entries have from 0, and this is the vector space over this. So, finite thing. Right. In fact, I'll leave it as an exercise to show this is easier to see. What is the dimension of NK in NK over K? It's vector space. These are n by n, so it should be like n squared.
Yeah.
How about this one? This is also, I can use a trick here. This is also n squared. This is And notice, this is a finite direct sum. So there's no distinction here between the direct sum and the direct product, right? Great. So this should be. Well, I can pull this out as a direct product. We go to homework exercise, we'll then the home, the direct sum, the first quarter pulls out the direct product. And I think that this is also the homework, home direct product, pulls out the direct product. Well, actually, let's do. That's- And what's home KK to this? Sometimes abstraction simplifies. You've already heard this. Actually. And remember, this is determined where field one goes, right? So this is isomorphic to the direct product. J one to N of the direct product, I one to N. Okay. So this is informal KDN squared. Okay. But the important thing really is, I think we can all get on board with this. These two are finite dimensional KDN places. This one, infinite dimension. So let's consider the following map. Uh, P and KX is home given by well, I'm gonna do something sagacious with whatever I plug in at. Right, my input here is some polynomial f and k of x. And what do? Well, how about plugging in the homomorphism, my fixed homomorphism? And what do I get? So for example, if f is equal to a n x n plus 1 x equals 0, then this is a n and I think we all know what a constant linear transformation is, right? It's a scale something linear transformation. And earlier, I mean that A0 times the identity linear transformation from E to E, right? This is in because my original phi goes from E to E, so any composition of it, so the composition or the power of it, which means composition here makes sense. Phi at the end, I just compose it at the same time. Okay. Any questions on that? So what do I know about this? This is infinite dimensional. And this is finite dimensional. And so actually the image of this will be a subspace of this, so it'll be even potentially even smaller. I don't know much, but I know this cannot possibly be 1 to 1. Right? Map cannot possibly be 0. And it's 90. Right? Because of course if I have two polynomials F1 and F2, such that this F1, F2 evaluated at the same equal 0. This is true for the sum because it's pointwise, right? And certainly if F is in the kernel and I multiply that by a polynomial K, then KF is also in the kernel. So this is a
So we know that this is a formula.
should we go through the details of that?
Right?
What's that now?
Formula. So if we say that that the kernel is 0 before this not 0, and we know that this is the formula. I mean, we're supposed to.
Okay. So you're evaluating this linear trend, just like the point, so that's the way point lines do this. Right. And also, right. But, so. Uh, kernel, some morphism. then for all K, E, K, X. And I didn't show the activity part, so it's an ideal and. Is that? Is that okay? Yes. Right, so this is, so you have the product of two polynomials, right? Evaluated somewhere, just like X, right? Then what that means is that not composition. No, it's multiplication, because what you're doing, you're composing that linear transformation with itself, so order doesn't matter. Right? So you can think of it as composition, right? But, so for example, if, let's give concrete examples of how it works. Let f of x, f1 of x, x1, and f2 of x. Four. Then, well, the product of these polynomials is x cubed squared, which in our case would be phi cubed plus b squared plus 2phi plus 2 identity. Which is actually p squared plus 2 identity. Right. And the powers here are compositions, but of course the order doesn't matter because it's just the power of a single linear transformation. So these all commute with each other. Does that make it a little better? Okay. So the kernel, as per the observations earlier, and this, of course, is in KX. We've seen that this is an ideal. And what do you know about the structure of KX from a ring theoretic point of view? This is the non-zero principal ideal, right? So this thing, principal idea, it's the kernel is generated by non-zero polynomial, right? Now, that polynomial can have any coefficient of its leading term as one. But you can adjust that to be one. And once you declare the leading coefficient as one, then it's unique, but there's only one generator. If you demand it to be mono. Okay, so far. Note that by the very definition, because remember, this thing generates the kernel of phi. So that means that when I plug in phi to this polynomial, I have to get zero. And if f is such that f of phi equals zero, then f is in the kernel this thing, which is generated by phi. So okay, so same argument goes along with A. So you can go through and get the same argument here. And if the polynomials are the same, then you get the Q phi equals QA plus. Now, let me also point out that phi are like on home K. I wouldn't care that much. Now, I'm gonna tell you how it works, right? So K of X is my scalar, and let's suppose I want to multiply. So this is a vector in E, which is where I claim that I have my KX modules. Let's let F of X be in KX. Now, I've got to come up with some cool way to take a polynomial and multiply it by E and get an output. Any ideas?
Do you have to be?
There you go. E is an element of the vector space. One good way to act on this is use a linear transformation. So I'm going to use my tool phi, plug it into this polynomial and get a bigger, fancier transformation, and then see what it does to E. So this is the way the action works. Polynomial times E, plug in this. Let's go through and verify this. Well, we know that E is a group, so no problem there. We need to Okay, it does land in the module, that's what I want, because phi takes E to E, so any power of phi takes E to E. So this, its output is where I want it to be. Notice that f of x, is f of phi, p1 plus p2. And of course, f of phi is linear transformation, so I can break that up. And so this is f of x p1 so my scalar multiplication plays well with addition. Also, this is f of x acting on g of p of e. And of course, this is a new element of e, so this is f of p e p v. And this is f of p g of p acting on e, which is basically f of x, g of x. So my associativity works, and I guess be really careful. Right, because this goes to the identity transformation on the image. Okay. Any questions? Right, and let me also point out that of course order doesn't matter if I've got, if my linear transformation here is fixed. Right, whether I do FG or GF, because when I compose the transformations, I just have powers of phi. Powers of phi can either themselves. Now that I've got this R module or this KX module structure on E, we say a K subspace of E is phi invariant. So I said this has got a phi invariant subspace if so in other words, if the linear transformation phi, I don't say it fixes F, but what I say is it keeps it, it's like Vegas. Everything in Vegas stays in Vegas. Right? So here's E, here's F. Every linear transformation just moves stuff around in F. Right? You don't leave. Right? Everything in F stays in F. Right? That's what it means to be invariant. Can anybody give me a phi invariant subspace automatically? We got the extreme twins here, 0 and E. Both of those are correct, right? Those will both be phi invariant, subspaces. From the point of view of the module structure, probably, we might say that, F is a KX submodule. Because if X is what choice, let's say if A is in F, then notice that when I apply phi to A, it's still an F. And so if I apply any power of phi to A, it's still an F. And conversely, if it's a K of X module structure, you can just take a simple polynomial here to show that it has to be phi invariant. Here is another kind of phi invariant subspace. Special sort of subject. We need the terminology for it. Let's let V be an element of E. So I'll pick some V and E out of this particular subspace. I'm going to call E V phi. This is defined to be the span of set So in other words, this is the invariant. Notice that E V P is spanned by so if you apply phi to any element, and alpha is the sum of Ki P P Phi P. Typical element of this looks like a finite linear combination. Some of those basis elements, well, basis is a poor choice, those generating elements. And notice that phi alpha is the sum, 0 Ki B alpha plus 1B, which is still in. So E V phi is phi invariant. When I apply phi to it, it's still the resulting element is still inside of that space. And this is actually called the phi cyclic subspace. By the way, before we get into it formally, let me ask you this. That's a spanning set, right? Notice that those dots are my dramatic way of going on forever. Do I need infinitely many?
Need to find the dimension of them more.
That's right. It says to stop at some point, right? So, in fact, if he is in dimensional, then if I look at the set B, B squared B, B, and B. This is linearly dependent. Right? Because this is a set of n plus one elements, so it has to be linearly dependent, right? What does this mean? Well, this means that B in B can be written as some linear combination of previous. And this is a polynomial relationship, right? That is to say, this phi v satisfies some degree in polynomial over K. And that's actually kind of an important observation. Okay, any questions? All right. I'm going to give you the theorem. So this is kind of the big theorem. This is the application of, well, any questions? Okay, so now we've talked about this. We've seen some familiar things come up. We've observed that these, there's some minimal polynomial for these linear transformations, et cetera, et cetera. So here's the theorem that really kind of ties it all together. And then we're going to spend some time showing you how to use it. So the theorem. And 723. And there are parts of this, in fact, a good chunk of this, that should look very much like the theorem of finite generated modules over PID. That's because that's what this is essentially. Let phi from ED be a linear transformation of finite vector space E over K. Linear transformation of a finite dimensional vector space over E over K. Number one, there are monic polynomials. Let's call them something. Q1 up to QT in K. One, Q2, QT, okay, X. And phi cyclic subspaces I will call them something E1 up to ET. B. such that E is the direct sum of these. And Q1 divides Q of Q2. Furthermore, QI is the minimal polynomial if restricted to EI. E, EI from EI. EI. And QT is minimal polynomial. This sequence of polynomials is completely determined by phi. And this is the invariant factor decomposition. As you might guess, there's an elementary boundary decomposition. It's similar what we've seen for pages. Two, there exists monic irreducible polynomials. Let's say P1 up to PS. AX. And P cyclic subspaces, Dij. The indexes I go up through S. So these indices, each one of these, the I corresponds to BI, and J is between 1 and KI. Such that E is isomorphic to and for every I, right, and for every I, there exists ethers. Let's say MI1, MI2. H5. Greater than 0, such that EI, the MI, MIJ is the minimum polynomial. Of P figure to Bij. Bij itself. And these numbers are, this is the element divisor. Do you remember when I did the fundamental theorem of finite generator abelian groups and I broke this up? Remember how we put each of the P CELOS subgroups up? Well, each one of these counters here corresponds to basically P CELOS subgroup. These things correspond to powers of a single irreducible prime polynomial. So that's why this one's a little bit more complicated to write down than the invariant factors. So, now, here is, and I can show you how this works via computation essentially. And we'll talk about this next time. So this is what this is basically the fundamental theorem of finitely generated abelian groups all over again. In this theorem here, I'll show you how this corresponds to the matrix. Let's first assume that phi is a linear transformation. Then V is that should be E. E is phi cyclic with minimal polynomial. Minimal polynomial. X to the R plus AR minus 1. A1 X plus A0 has that minimal polynomial. If and only if the dimension of V is R, and there exists basis for E such that the matrix P is given by this. So 1, 0, 0, 0, 0. So 2, 0, 0, 1. And finally, I'll explain why this is true next time. By the way, I write about matrices in this form because that's the way I'm used to it. To prove this theorem, the way this matrix works is this takes row vectors multiplied on the left. This is the way the theorem works, and I apologize for that. If you want to get this canonical form so that you multiply column vectors on the right, just to have to take a transpose of this. So anyway, we'll talk about this next time. Any questions? Any questions? All right, well, I will see you folks on Friday.